Welcome viewers. Today we have a topic before us and it's design of footing. And today we want to be doing an illustrative example of how we can be able to design a footing. And we have a problem on the board, and the problem is thus that the reinforced concrete base is required for a 225 by 225 column. Now carrying a dead load GK of 500 kilonewton and a live load QK of 350 kilonewton. All right, so we have this question we want to solve for the bearing, for the design of this footing. Now, apart from the dead load and live load which was given, we also have that the base will be supported on a soil of depth, and the soil has a unit weight of 18 kilonewton per cubic meter. We have the internal angle of friction of the soil to be 23 degrees and the shear strength coefficient C to be 16 kilonewton per meter square. Now we intend to design this footing against a bearing capacity failure for a factor of safety of 3.0. We are going to design it against bearing capacity failure. We have the characteristic cube stress of concrete to be 25 Newton per millimeter square. We have the characteristic strength of steel, which is 410 Newton per millimeter square. All right. So today we want to do this design based on the British Code of Practice BS8110 1997. We are going to be using that code to carry out this design. Now, in solving this problem, the first thing we must note is that we have the load given on the board are the axial load that is being carried by this column. And we are told that the total dead load is 500 kilonewton, while the live load is 350. These loads are unfactored load, they are service load. So since they are service load, we can now say that the total service load for this particular footing, we have it to be 1.0 GK plus 1.0 QK gives us the total service load of this footing. Now I said that the total service load becomes 850. All right, that is the total service load carried by the column. Now in this 850 of the total service load, remember the footing itself has its own self weight. We do not know the self weight of the footing because at this stage of the design we've not been able to determine the size of the footing, talking about the breadth, the length, and the depth of the footing. Because for us to be able to obtain the self weight of the footing, we need the thickness of the footing as well as the surface dimension. Now we've not gotten that. So what we are going to do for this preliminary stage of the design is to make an assumption. Most likely I will encourage you to make use of 15% for your self weight of footing, like as I've done. Say 15% of the total dead load, let it be the self weight of our footing. So if we work 15% of the total dead load, which is 500, we'll have the self weight of the footing to be 75 kilonewton. Okay. Now, I haven't gotten the 75 kilonewton, which represent our footing self weight. The next thing we want to look at is the depth. From the question, you can see that we are not given the depth of the foundation. We do not know the depth. So, of course, we just assume that the foundation, we are going to excavate the foundation to a depth of about 1.2 meters from the surface, from the ground surface. So that is the assumption. So I said assume that the foundation depth is 1.2 meter. So that 1.2 meter is from the ground surface. Now the next thing I'm going to assume the dimension of the base, like we said, we've not known it. And we need to choose whether we're going to use rectangular base or we're going to use a square base. But I would prefer a square base, and I will encourage you to do a square base, especially when it becomes very, very necessary for you to do a simple and a smart design. So I have my base dimension to be B times B for a square base, where B represents the dimension of the base in meters. Okay. Now, we've taken the self weight of the footing, which represents 15% of the dead load at 75 kilonewton. So we're going to have the total gravity load, including the self weight. So if we do that, gravity load, the total gravity load at this point on the soil becomes 1.0 GK plus 1.0 QK. In this case, that I'm introducing the self weight of the footing. So for my total dead load, it becomes 575. And if I have that, my total service load becomes 925 kilonewton. All right. So this is the load that the soil is about to sustain, 925 kilonewton. Now, while we're using service load, whenever you are designing, you are about to size a footing. For sizing of the footing, you must make use of your service load. Okay. Now, when it comes to the design of the footing proper, you must make use of your ultimate load. Now, we've gotten our total service load to be 925. Now let's look for the bearing capacity of this soil. That is the next stage of the design. Now, how do we obtain the bearing capacity of the soil? Now, we're going to make use of Tazaki's bearing capacity equation. And we have the general equation for Tazaki's bearing capacity to be Q is equal to 1 over 2 gamma N gamma B plus Q naught bracket NQ minus 1 plus NCC. All right. So this formula represents the general what equation for Tazaki's bearing capacity. All right. Now, in applying the formula, like I've said in our previous lectures, we need to know what shape of footing are we working on. Is it a square footing? Is it a circular footing? Is it a rectangular footing? But in this case, I've already chosen a square footing, so I'm going to apply what we call the shape factor, which are coefficients that will be used to multiply each of these three expressions, talking about this, talking about this, and talking about this. So the shape factor in the case of a square footing is for us to get the aspect ratio. The aspect ratio is the breadth over breadth. So in this case, we have B over L, where L represents our B. So B over B becomes 1. So 1 times 0.2 minus 1 will give us 0.8. Similarly, our XC, which is our shape factor for shear, becomes 1.1 plus 0.3 B over L, which is present 1. It becomes 1.3, and SQ is generally 1.0. All right. So having gotten this shape factor, we're going to multiply each of them by our coefficient by this term. We multiply this by this. We multiply this by this. Okay. So having done that, we are going to have the final expression here. You can see I'm writing it. In this case, I'm applying the shape factor S gamma, applying the shape factor SQ, and I'm applying the shape factor SC. Okay? So the general formula becomes this once the shape factors have been applied. Now, we look back to the question. We've been given the internal angle of friction of the soil. That angle is 23 degrees. We read it from the chart. When we read it from the chart, you can look at the charts. From the chart, you will see that we have NR to be 7.4, NC to be 21.74, and NQ to be 10.23. All these are the Tazaki parameter for internal angle of friction of 23 degrees. All right. So when we read it off, we have all these values. Now, the next thing we're going to do is to plug in these values into our general equation for Tazaki's bearing capacity formula. So if we put it, we're going to have, substitute these values into it. We'll have, for the shape factor for gamma, 0.8 is here. For the shape factor for shear strength, we'll have it as NC, we'll have it to be here. While we'll have the shape factor for overburden, we have it to be 1. We have it to be here. All right. So if we solve the net bearing capacity, you solve this one, you're going to have 53.28 B plus 199. Remember, the B represents the breadth of the footing. Okay. So solving this equation amicably, we are going to have our net bearing capacity to be 53.28 B plus 199.368 plus 452.192. So solving this, we are going to have our ultimate bearing capacity, our net bearing capacity as this. Now, we are going to have, for us to have the safe bearing capacity, of course, we are going to reduce the bearing capacity by dividing it by our factor of safety of 3.0. So reducing it by dividing it, we are going to have this as our final safe bearing capacity. Now this safe, all right, so the safe bearing capacity of the soil is this. Now, the next thing we are going to do is sizing of the footing. So say proportioning of footing. So we want to proportion this footing Now, the first thing we want to check is the punching shear requirement. Now, the punching shear requirement is that the breadth of the footing, B, must be greater than the column size plus 3h. All right. So this is a punching shear requirement. This punching shear requirement requires that the column size plus 3h, the breadth of the footing must be greater than the column size plus 3h. For punching shear requirements. So this is what we have for punching shear requirement. So we know that B must be greater than the column size plus the distance from the critical. Now this column size could either be the breadth or the length. If you have a rectangular column, whichever you have, whether a rectangular column or you're having a square column. So if you're having a square column, you do that too. It represents the similar thing. So now let's go on with that. So with this, we can size our footing. We can pick a thickness for our footing and choose the necessary corresponding breadth of the footing. So for in this case of our design, we are going to assume, let's assume thickness of footing h to be equal to, let's try 300 millimeter. Okay, let's try 300 millimeters. So let's assume this is our thickness of footing. What it means is that the required breadth of the footing should be B greater than, we're assuming a square. We already know it's a square column, so we have one side of it, which is 225 plus 3h, 3 times h. Our h in this case, we have assumed 300, so we have 300. Okay, so what we are saying is that the breadth of our footing, this become 900, this become, we are saying that the punching shear B, our breadth becomes we have 1125 millimeter as our value there. So now, having gotten this value, we are going to choose value for our breadth. So we say choose B to be equal to 1.4 meters. Okay, 1.4 meters. So I will choose my B to be 1.4 meters. It means that the dimension of footing becomes 1,400. We now have 1,400 mm by 1,400 mm by 0.3 meter depth as our dimension of footing. Now we have chosen this footing. We are not going to stop here. The next stage you are going to go into is, having chosen this footing, we are going to check for stability requirement. All right. Now for stability requirement, we know that the total stress due to service load from gravity load must be lesser than the safe bearing pressure the soil can carry. Okay, so that is the requirement for stability. So the total load due to service load, the total gravity load, which is a service load, is, say, for stability requirement, So for stability requirement, we say that total stress due to service load must be lesser or equal to total stress allowable or safe bearing pressure of soil. All right, so this is a stability requirement. So once we are able to get the total service load, it is expected that this total service load uh, must act on the soil. So this total load is going to be inducing stress on the soil, and the area of that load, the load will be acting is equal to the area of our footing. And if we do that, we can get the stress induced on the soil due to this load. And that stress induced on the soil due to this load must be lesser or equal to the total allowable bearing capacity of the soil, or the safe bearing pressure the soil can be able to sustain. All right. So if we do that mathematically, what we are saying is that we'll have our total uh, stress due to service load as this, which is 925 by uh, 1.4 by 1.4. This is the stress. So we are saying that that stress must be lesser than the safe bearing stress of the soil, or safe allowable bearing capacity of the soil. And we've gotten that to be our expression on the board on this side. I remember here we have B in this place, so we're going to substitute the value of our breadth of footing. So if we plug that in, we should have this expression to become 53.28 times 1.4 plus 65 1.56 all over 3.0, which is a factor of safety, like we've gotten it before. So we're going to check out to see if actually the stress from this load is actually lesser than this value we are going to have on the right hand side of our inequality. So that we are going to check out to be sure. If it's not lesser, we need to increase the size of this footing to ensure that it meets up with this requirement. Okay. All right. So having done this, you can see the pressure. Solving this one, we're going to have 471.9 kilonewton, 0.93 kilonewton per square meter. While here we have here to be 240.05 kilonewton per square meter. Of course, you will see that this figure is greater than this. So saying that this is lesser than this is not going to work. So we asterisk it. It means that the dimension of 1.4 by 1.4 is not going to satisfy our stability check. So we're going to choose another dimension greater than 1.4. So let's assume you can see the difference between the figure almost times 2. So we should pick a figure, let's say around 2.4. If we choose a figure around 2.4 meters, so adding additional 1 meter to it. Let's see how it works. Now, if we do that, we're going to have this thing again to the T requirement again. Our stability requirement says our 925 over 2.4 by 2.4. We said that it must be lesser than 53 point divided by 3.0. Okay, so having our total applied stress on the footing to be 160.59 kilonewton per square meter, while the allowable stress that the footing can carry is 259.81 kilonewton per meter square. So it means that the footing can conveniently carry this load because this one is greater than the applied load that is coming on the footing. All right. So it means at this stage our footing has satisfied stability requirement. So this is the first stage. So it means that our breadth of footing of 2.4 meter by 2.4 meter by 300 is satisfactorily okay for this design. So we say that hence 2.4 meter by 2.4 meter by 0.3 meter size of footing will satisfy stability requirement. All right. So obviously it's both shear stress requirement and punchy shear requirement. Now the next thing we are going to do, having gotten all this, we've chosen the size of the footing. The next stage, we are going to look for what we call the base reactive pressure of this footing. All right, so the next stage we are going to look at is the design for reinforcement. And like you can see from the board, we have this column, we have the load acting on the column, GK. This is the ultimate load acting on the column. Now, when we have this kind of column that is acting concentrically at the centroid of your footing, we are going to have the pressure on the footing to be uniform, okay? So like you can see, when this load, gravity load comes up, it will result to some sort of bending at the edge of the footing. Now, this part of the column will act as a what? As a cantilever. So we have a cantilever. This is assumed to be a column. Of course, this is a column. So we have it bending in one direction due to pressure and due to the load acting at this point. So we're going to have pressure, upward pressure from the soil acting to cause an upthrust in the footing. All right. So if we have a situation like this, and we know that the load is acting, the resultant load is acting at the centroid of the footing, we are going to have a uniform distribution of pressure. All right. So the pressure is going to be acting on the footing uniformly. So that pressure that is acting on the footing is what is known as the base reactive pressure. These are pressure from the soil acting against the footing. As the pressure from the column presses down, it causes a what? An upthrust force on this direction. Okay, so we're going to have the load acting at this point to work as a cantilever. So the cantilever goes like this. This is assumed to be the support of the cantilever. So the footing is acting at the cantilever, um, um, sourcing from the centroid of the footing. Okay. So when we have this, like I said, we are going to design this, use this design load for the ultimate limit state. So the ultimate limit state, we make use of 1.4 GK plus 1.6 QK according to BS8110. So we can now say that the total pressure acting on this soil is pressure, we can say pressure from gravity load equal to our base reactive pressure. Okay. All right. So the amount of pressure that is induced on the base due to the gravity load from the column will be equal to the amount of pressure that will cause a bending in this direction of our footing. All right. So let's calculate, and that pressure is what we call the base reactive pressure. So now let's calculate that base reactive pressure. So we can say that the base reactive pressure is equal to our ultimate load over the cross-sectional area that this load is acting on, and that cross-sectional area represents the area of the footing surface. All right, so the surface of the footing itself, we have that area to become 2.4. Now let's get the total axial load. So this arrangement represents a concentric column, meaning that the column is acting at the centroid of the footing surface. So, but in some cases, we might have what we call an eccentric column, a situation whereby the column is placed at an eccentricity from the centroid of the surface of your footing. In that case, you are going to have some level of variation in terms of your base reactive pressure. Okay, so let's do this. We'll come to that when we are treating eccentric column. Now we have the total axial load from this to be, all right, calculating the base reactive pressure. We say that the ultimate base reactive pressure NU over A, which NU represents our ultimate load. So let's calculate the ultimate load. We have N equal to this. We have the ultimate load to be 1365 as the ultimate load. Now we're going to calculate the base reactive pressure. Now in calculating the base reactive pressure, like I said, base reactive pressure becomes equal to 1365. So if we stop this out, we're going to have it to be 236 kilonewton per meter one square. All right. So this becomes the base reactive pressure. Now this pressure is going to be active uniformly over the surface of the footing. All right. Now in designing the footing, we're going to design it as a two-way slab, like you can see from the board. We'll just pick a strip of 1 meter from this footing and design it as a beam. Okay. So it's going to be treated as a cantilever slab. Let's obtain the pressure from the total service pressure, and we say that total service load divided by the section, the surface area of the footing, which represent the cross section. And if we do that, we're going to have the service pressure to be 160.59 kilonewton per square meter. And if you check, you will discover that that same pressure, when we substitute the value of our size of footing of 2.4, will have this total applied service pressure to be less than the safe pressure of the soil. All right. So by this we know that at this point the dimension of 2.4 by 2.4 by 0.3 meter is adequate for the design in terms of stability requirement. But remember that we need to check 0.3 meter also to be sure that it will scale through the punching shear requirement. As we continue in the design, we're going to check that out. If our depth of footing, which is 0.3 meter, we satisfy the punching shear requirement for this design according to our code. Now let's go over to the loading of the footing. Now the loading of the footing, we are going to load the footing using our ultimate load from column. All right, so our ultimate load from column according to our code, 1.4 GK plus 1.6 QK, 1.4 GK, where GK represents our total dead load and QK represents our total imposed life load. Now, like we know that the pressure acting in the form of gravity load is equal to the pressure that is causing an upward force on the footing. We know from basic knowledge of force that for every force or every action, we have equal and opposite reaction. So as we have the gravity load coming down on our concrete footing, provided that the base remains stable, what you are going to have is that it's going to induce some upward pressure on the sides of the footing. All right. So these pressures that are acting on the sides of the footing is what we call the base reactive pressure. Now the pressure from the gravity is equal to the base reactive pressure. Now I said that the base reactive pressure NU is equal to NU over A, where NU represents the ultimate load and A represents the surface area of our footing, which we have as 2.4 by 2.4. You can decide to make use of 10%, but I will prefer using 15%. So the total dead load will have it to be 575 kilonewton. All right. Total life load is 350. So the total ultimate load is 1,365 kilonewton. All right. So having gotten this total ultimate load, we are going to look for the pressure, the surface area the load is acting on, which is the surface of the footing, which is 2.4 by 2.4 meters. All right. So now, apart from this load, we have the total load is this, but inside of this load, we are going to look for the load due to the self weight of this particular footing. We are going to subtract it from the total ultimate load that is coming on that footing. So let's look at the stress due to this ultimate load. All right. So The total stress, the base reactive pressure, which represents our QB, let's call it our QB because of N over A, we have the total base reactive pressure to be 236.97 kilonewton per meter square. Now, we need to look for the net pressure, the net upward pressure. Remember, this pressure is going up, but we need to remove the pressure, the force due to the self weight of the footing, which is a gravity pressure. So if we do that, we make use of the self weight of the footing. Remember that the thickness of the footing is 0.3. So we have 24 times 0.3. We factor it. When we factor it, we're going to have 10.08 kilonewton per meter square. So I will apply factor of safety of 1.4. We subtract it to obtain the net upward pressure that is acting on the footing. When we do that, we're going to have 226.89 kilonewton per meter square. All right. So this is what we call the base reactive pressure. But remember that we are not too sure if our punching shear requirement has been satisfied because we have a base of thickness of 0.3. So we're going to ensure we check out for punching to ensure that our footing satisfy punching shear requirement. Okay, so we'll do that later. Now let's go over to the idealization of the footing for our design. Now, looking at the footing at this point, you will discover that the center of the footing, let's call the axis of the footing, this is x axis, this is y axis. Now, if you divide the footing equally, this is the center. Now, it is believed that, like we've demonstrated in the other chart, you will see that the footing is acting as a cantilever spanning from the column. All right. So from here to here is the column. Now let's assume that the load acting on the entire surface of the footing, let's call it QB, which represents the base reactive pressure that is acting on the entire surface of the footing. So if we pick a strip of 1 meter from the footing, we are going to have that strip like this, as 1 meter strip width. We are going to have it as this. So this is the 1 meter strip width, and the length of that 1 meter strip is 1.2 meter, because the total from this point from here to here is 2.4. So if we divide this into 2, we'll have 1.2 meter as the length of that cantilever. So this is the cantilever we are going to solve for moment, using this cantilever to solve for moment. And also we can decide to also check the value for shear. All right. So the next stage we want to do is to check for punching. Remember, like I said, we are going to check for two-way shear. The two-way shear is also called the punching shear check. All right. So remember, this is 2.4. We have this 2.4. Now, according to the code, we have 1.5H from here, where this represents our critical perimeter. The whole of this represents our critical perimeter. Now, the shaded area there is the area we're interested in. That is the area outside the critical perimeter. So we're going to get the stress acting on that point. Now, for us to calculate punching shear, we know that punching shear is punching shear stress is our V over our critical perimeter times effective depth. All right. The V in this case represents the value for the shear outside the critical perimeter, which is the value for the force acting on this shaded area. Okay. So for us to get that force acting on this shaded area, we already know the formula for calculating the area of this shaded area. And we already equally know the total forces that are acting on the entire surface. So we can easily calculate the force that is acting on the shaded area and plug it into this place. We've already know what our critical perimeter is from the formula for deriving critical perimeter. We can obtain our effective depth. So we can check out for this to know if this will satisfy our punching shear requirement. Okay, so I said the total force acting on the entire footing is 226.8 kilonewton per square meter. So that gives us the total force acting on the entire footing. I haven't gotten the total force acting on the entire footing. Let's go over and determine the shaded area of this shape. If the total force acting on the footing, we have it to be 228.8 kilonewton per meter square. We are saying that let's call that force QB. That force is lesser than 259.8 kilonewton meter square, which is the force that is being representing the bearing stress or bearing pressure of the soil. So since it is lesser, the ultimate bearing pressure of the soil, it means that requirement is okay. Now, the next thing we are saying is that the area inside the critical perimeter, remember the formula AS plus 3H all square. Remember we derived this formula before from our first one of our videos. We're able to derive it. Now, the area becomes this. When we solve for that area of the which represents the area of the shape inside, we are going to calculate the area of the shape outside. Okay, now how do we do that? As the area, this is the area of the unshaded region, which is the area inside within the critical perimeter. So that area becomes the area of the unshaded portion, which is 109,2042 mm square as the area of the unshaded portion. Now, the area of the shaded portion will be the area of the total square footing minus the area of the unshaded portion, and the area of the total square footing is this. So all we need to do is to remove this from this, and if we do that, we are going to have it as the area of the shaded portion, which represent the failure zone. I said the area of the shaded portion represented the failure zone of punching. That area becomes the total area of the square footing minus the area of the unshaded part, and that gives us the area of the shaded part. Okay, that is 46679 58 mm square. All right, now this is the area we're interested in. Now what will be the equivalent load that is acting on this area if we have the total pressure that is acting on that area to be 226.85? Now what we are saying is that we're going to express that thing in newtons. So I've changed this pressure 226.897 to newton per millimeter square, so we can have that value in newton per millimeter. So if we solve that out, we are going to have that force acting on the shaded area to be 1059145.66 Newton. All right. Now, having gotten that force, we need to obtain the critical perimeter CP. We know from our derivation also that the critical perimeter is the column perimeter plus 3 pi h. So if we solve that amicably, we are going to have it to be 378.52 mm as the critical perimeter. Now, having solved for this, the next stage we are going to work on is to check the punching shear. All right. When we've through with the punching shear, we'll come back to design the footing. All right. So let's check for the punching shear in this case. Remember that punching shear stress is equal to the force acting at the failure zone, which is the zone, the shaded area, over the critical perimeter times the effective depth. Remember, we've gotten the effective depth, the total depth of footing. We can say the effective depth D is equals to depth of footing minus, let's have diameter of bar minus our cover. All right. So we can have our D to be 300 minus 20 over 2 minus 50. So at this point, we are assuming a cover of 2 inches, which is 50 mm, and approximately 50 mm, and we are assuming a reinforcing bar of 20. So we can say that our cover becomes 10, which becomes 240 mm. All right, so this represents our effective depth. So once we've gotten the effective depth and we've gotten the critical perimeter and the force acting outside the critical perimeter, we can now get the shear stress. We'll have that the shear stress, punching shear stress becomes the total force acting. We've gotten that before to be 1059145 0.6 divided by critical perimeter, we have it to be 3728.52 times. We have our effective depth to be 240. All right. So we'll solve this out and let's find out what our punching shear is. Okay. Remember, once we are done with check of the punching shear, we are going to solve for moment for this cantilever representing the main reinforcement for this footing. Okay. So let's check out the stress. Now, remember that according to our code, that this punching shear stress should be lesser than 5 Newton per millimeter square, or 0.8 the square root of our FCU according to BS8110. So we'll check that out to see if that is satisfied. Once that is satisfied, we are good to go. All right, so once we solve for this, so our shear punching, all right, so our punching shear becomes 1.183 Newton per millimeter square, and this is less than the lesser of any of them. The lesser of this is 0.8, the square root of our FCU. Remember that our FCU that was given is 25 Newton per millimeter square. So if we check that out, you will agree that it's lesser than that. So this makes our section adequate. So you can therefore say that section footing is adequate in punching shear. Therefore say that the footing is adequate when it comes to punching. Okay, so the next thing we are going to do is to check for our one-way shear, which we call a one-way shear, which is the same thing as our transverse shear. All right, so let's look for that of the transverse shear. We have now we can say that the footing is adequate in punching shear. Now the next stage is we are going to check for transverse shear. Now, like we see, according to our code, our transverse shear, the area affected by transverse shear is the shaded area. So we need to get the stress acting on this area, the pressure on this area. So if you look at what I've done, 1.5D from the face of our column, we'll have D to be 240, 1.5D becomes 360 mm, and we'll have this section to be 727.5 millimeter. So that is the area we'll have our pressure acting at. So if our pressure is acting at this point, now the idealization of our footing, you can see the idealization of our footing, you can see the cantilever here. So this is the region we're interested in. So, but if we apply the load, the restraining load at this point, we'll have the shear force expression, we'll have the support reaction here to be 2 minus 2, let's call it plus 272.268 as the reaction. Let's call the reaction here to be positive. This is negative. So if we work this out, we're going to have this. So when we write the shear force expression, this becomes our load 22.6, and so this become our load 22. This become our load 226.89. Now the shear force expression for this idealized section is this, where we have the force acting upwards to be negative, the one acting down to be positive. So we have this expression. So the distance from the face of our, from this point to here, we have that figure. From the center line from this point to here, we have that figure to be 0.4725. So from this center line of our column to the face of the point where we have the transverse shear, we have it to be 0.725 meters. So from this point, is where we're interested in, the shaded area as well. So the shear force from this point is what we're interested in. And if we solve that out, we'll have the shear force to be what? To be, substitute the value of S, which represents 0.7425. We'll have the shear force to be 165 kilonewton per meter. Now that is the shear force we want to check for transverse shear. So that shear, we're going to find the shear stress for that. The equivalent shear stress for that is 165 times the breadth, uh, 165 times the uh, times 1000. We're expressing it in Newton per millimeter square. So multiply by 1000 divided by effective depth D times the length of this side, this portion of the area, which is this length. All right. And that length is 2.4. So we do that. If we do that, we have 0.28 Newton per millimeter square, which is less than the allowable transverse shear required by our code. So we say that this footing has been able to scale through the orders of transverse shear. Now, the last thing we are going to do in this design is to design for the reinforcement. Now, which is the design of the reinforcement. Now, you can see the cantilever like usual. The moment it becomes this, we have 163.6 kilonewton per meter per unit per a meter weight of slab. So if we solve that out, we're going to have the total area of steel required, say area of steel required to be 2055.17 mm square per a meter width of slab. So we say provide Y20 at 150 center to center, and area of steel provided is 2090 mm square for both sides of the footing. All right. So with this we have done, I believe we'll be able to take on the design of a footing conveniently. If we do have any question bothering us concerning all we have done, please do well to email me. You can get my email and send me a message on my email. Or if you do enjoy this lecture, do well to hit the subscribe button and click the like section. I hope to see you in our next class. Have a wonderful day and God bless you.